As was just previously mentioned by Dedri, we very frequently use spatial words to talk about abstract concepts. So these types of spatial metaphors are extremely pervasive. Across languages and cultures, we use spatial language to talk about all types of non-spatial things. So we can use space to talk about time. We could say they went on a long vacation. We can use space to talk about things like emotional valence. We can say something like things are looking up today. We can also use space to talk about things like musical pitch. So we could say something like she sang a high note. And while these types of metaphors are very common across languages and cultures, the exact types of spatial references that are evoked in these metaphors can vary across languages. So in languages like English, we might talk about musical pitch in terms of vertical height. So notes could be high or low. Where in other languages like Turkish or Farsi, we could say something like she sang a thick note. So we would use thickness to describe musical pitch. And even if this metaphor is unfamiliar to you, you might have some kind of intuition about how a thick note matches onto pitch. So in my research, I'm very interested in what these types of metaphors can tell us about the way we represent these non-spatial dimensions and advantages that might be at play by using space to talk about these other dimensions. And importantly, these metaphors are not just present in language. These types of metaphors are present in the way we actually think and represent about these domains. So it's not just for talking, it seems to be some deeper level of analogical structuring that's at play that's helping us understand these non-spatial domains. One of the most common ways that this has been shown, so we've seen these types of effects in a variety of nonverbal tasks. And one of the most common ones coming from Daniel Casasanto is showing that spatial information can bias the processing of more abstract domains. So for example, time or pitch. So for example, if you see a line appear on the screen and you need to reproduce either the physical length of the line or the temporal duration that you saw the line, people's judgments of temporal duration are influenced by the length of the line. So lines that are physically longer are judged to have been visible for a longer temporal duration than they actually were. And interestingly, we see that the type of information that seems to bias varies by language. So in English, when we can describe temporal duration in terms of length, other languages use more three-dimensional metaphors like you would say much time instead of a long time. And you see there that three-dimensional images tend to cause this biasing rather than just two-dimensional lines. But it's not just language that's creating these associations, because we see that infants already in the first year of life, and even in some really elegant work by Lola de Hevia, even neonates, so in the first few days of life, seem to already exhibit associations between space and other dimensions. So expecting that lines that are longer physically will also be visible for longer periods of time and also be associated with a greater number of items. So from this work, we see that language doesn't seem to create these types of associations between space and other domains, but it might reinforce them through the metaphors that we are using in our everyday language and experience. So today I'm going to be talking about space-time and space-time associations as a case study of how we can use space to reason about abstract concepts. And there are really two big questions that I'm interested in. One is about the types of cultural experiences that shape the development of these cross-dimensional associations. And the other is about why we use space to think about abstract concepts. I'm going to start with this first question. What are the types of cultural experiences that shape cross-dimensional associations? And critically, it's not just language. So although we use language and these types of spatial metaphors to talk about a lot of things, we can also see these types of spatial associations are present in other types of cultural artifacts. So for example, if I say Wednesday's meeting has been pushed 2 days to the left, when is the meeting, Monday or Friday? This is going to sound weird to you. We don't usually describe movement through time in the left-right axis, but you probably, again, have an intuition about when the meeting is. And this is because we're accessing something called the mental timeline, which is a mental model of time that's based on a linear reference frame. So this is a very common association between space and time. And in many Western cultures, this mental timeline is envisioned as a horizontal line going from left to right, with earlier events on the left and later events on the right. So if I show you a diagram like this, which is pretty abstract. We can get a sense that as time is passing, this cat is getting older. Whereas if it was oriented in this way, it would seem like there's some type of Benjamin Button situation going on where the cat might be decreasing in age over time. And although in many Western cultures, we orient the line as going from left to right, this orientation varies across cultures, frequently consistent with writing direction. So in other cultures, common mental timeline orientations could be from right to left or from top to bottom. But there are many ways that we can explicitly spatialize time, independent of language and independent of writing. And one of those is calendars, which are a way that we can represent the passage of time in a two-dimensional spatial format. And frequently, calendar orientation is consistent with writing direction within a culture. So in English, for example, we read from left to right, and on most common wall calendars, we'll see something like this, where the days of the week also go from left to right. But some cultures arrange their calendars in other ways independent of writing direction. So many of the most common languages in India, including Hindi, Gujarati, and Tamil, are presented from left to right. But we see in regions where these languages are common, calendars like this, where the days of the week are oriented vertically. So here we're seeing a dissociation between writing direction and explicit spatialization of time. And I'm very interested in how this dissociation may be reflected in how people orient their mental timelines in these cultures. A second type of representation of the passage of time occurs in the sagittal direction. So in addition to the mental timeline, which maps times onto a horizontal line with a perspective external to the body, sagittal representations map time onto the front-back axis, internal to the body, with the observer in the center of the axis. And in many cultures, the future is represented as being in front of the body and the past as behind the body. That could be consistent with locomotor experience through space and time. So as we move towards events in the future, we're also moving forward through time. However, other cultures endorse the reverse mapping with the future behind the body and the past in front, under the idea perhaps that the past is knowable and therefore it can be seen, but the future is unknown and therefore unseeable. And although we can see these types of dissociations in the orientation of these sagittal representations across cultures, within cultures, we can also see evidence for individual differences in how individuals map this sagittal axis. And this seems to be related to individuals' temporal focus, wherein individuals who are more focused on the past and perhaps more focused on traditional values, so individuals who might be more religiously conservative, or older individuals who might be more focused on the past might be more likely to map the past to the front, even if they are in a culture that uses front-future metaphors. So for example, in English, we say things like, we look forward to, upcoming vacation with the past in front, with the future in front, sorry. And we also gesture in ways that are consistent with these metaphors. In this first study that I want to talk about today, we were interested in how children are constructing their mental models of time, and specifically looking both at the mental timeline and these sagittal representations. We conducted this study in Gujarat, India, so we could take advantage of these differences in calendar layout. And we collected data from students between 1st and 9th grades who are between 6 and 15 years of age. And we had them do a few different tasks. So we had them do a timeline task, a temporal diagram task, a temporal focus questionnaire, and a calendar drawing task. Excuse me, and I'll talk about all these tasks in a moment. And the calendar drawing task was just to ensure that children were actually familiar with both of these calendar orientations. So these are example calendars that children drew, and we saw that both these horizontal and vertical calendar orientations were equally common in children's drawings. So this timeline task is adapted from Tillman, and it's a very elegant, very simple task. And what we did is we showed kids a piece of paper like this, and we put down a sticker in the middle. So we'd tell kids to say, think about the times when different days happen: yesterday, today, and tomorrow. I'm going to put a sticker down for today, and I want you to put stickers down for yesterday and tomorrow. And we would give kids these stickers to put down, and we counterbalanced whether the future or past event was asked first. And we had kids do this for yesterday, today, and tomorrow, and also morning, noon, and night. So these are some example timelines that children created. And we categorized the orientation of children's timelines. So common orientations were left to right, top to bottom, diagonal, which was along any diagonal axis, and then a few kinds of nonlinear. So stickers that were not chronological or stickers that had an angle of less than 140 degrees. As you can see, these were done with actual stickers. We also had children do this temporal diagram task that we adapted from De La Fuente and colleagues. On this task, kids were shown a diagram like this with a character in the middle and a box in front and behind the person. And they were told to put down stickers to remember when different events happen. So we would hear a story like this. Yesterday, Priya visited a friend who likes cats. Tomorrow, Priya is going to visit a friend who likes flowers. To help you remember, put the cat sticker in the box for yesterday. And now put the flower sticker in the box for tomorrow. And kids did this 4 different times so that we could assess children's individual consistency. And we also had them do 2 trials like this with the face pointing up and 2 trials like this with the face pointing down to ensure that kids were actually taking in the character's perspective into account, so the front and the back and not the verticality of the page. So because children did 4 different trials with the head facing both ways, there were a few different ways that they could end up answering. And so children needed to answer 3 out of 4 trials in the same way to be classified as either front future or front past, depending on where they put the stickers. And otherwise, they were classified as inconsistent. We also adapted the temporal focus questionnaire from De La Fuente and colleagues, where we asked older children in the 6th and 9th grades how much they agreed with different statements about the past and the future. So statements like, I think that young people should live their lives in the same way that their parents and grandparents did. So agreeing with this statement would be more past focused. Or a statement like, I think that new technologies like computers and cell phones make people happier, which would be a more future focused statement. Moving into the data, I'm going to show you here a stacked bar plot with the proportion of different types of lines that children created in the timeline task. So we have 1st, 3rd, 6th, and 9th grade along the x-axis, and then the different line types are in different colors. And there's a lot of line types, so there's a lot of colors. So this is what children's distribution of lines looked like. So starting on the left in the 1st grade children, we can see that that bar is mostly red. Children in the 1st grade mostly did not arrange the stickers in lines. But moving towards the right, by 6th and 9th grade, we can see that these periwinkle and green bars are becoming bigger. So we see that students at this age are most likely to make linear arrangements, and they're most likely making left to right and top to bottom lines. And they were equally likely to make these 2 types of lines. So we see that with age, kids are becoming more linear in their mental timelines, and they seem to be creating both left to right and top to bottom. So both horizontal and vertical timelines consistent with the types of calendars that they're experiencing in their environment. Next, looking at children's temporal diagram tasks, so where they're mapping the future. We see that in the 1st grade, children are actually mostly consistent in their responding. So children in the 1st grade and the 3rd grade are not responding at chance. They are internally consistent, but they are equally likely to map the future to the front or the future to the past. But again, with age, we see that this front future mapping, so the conventional mapping direction, is becoming more common. So by 9th grade, the majority of the children are making front future mappings. And then looking at this final question of the temporal focus questionnaire, we can split kids based on their responses on this survey to whether they were more past focused or more future focused, and see if that shifts, if there's differences in the diagram directions that were most common. And again, this is only in 6th and 9th grade students, and students in this age are predominantly front future mappers. But even so, we can see that among children who scored as more past focused on our temporal focus questionnaire, these children are more likely to map the past to the front. So we see that although older children overall are mapping the future to the front, their responses on this temporal focus survey are predicting individual variation. Oops. So in our question of what types of experiences influence spatial temporal associations, We see that the mental timeline is becoming increasingly linear with age as children are gaining exposure to formal schooling and cultural artifacts like calendars. And we see that both writing direction and calendar orientation seem to influence the orientation of the mental timeline. We also see that sagittal representations are becoming increasingly aligned with cultural conventions with age, and that temporal focus has some influence on individual differences in sagittal mappings. So in general, we see that children are sensitive to both cultural and individual factors when they're creating their three-dimensional mental models of time, and they're becoming increasingly aligned with cultural conventions with age. The second question that I'm really interested in is, why do we think about abstract concepts in terms of space? So these spatial metaphors and spatial associations are clearly very common, but it's not exactly clear why this is. So in the next part of my talk, I'm going to look at two examples in language learning and memory to try to explain why these types of metaphors might be so common. So as I've been saying, spatial metaphors are very common. And one reason why we hypothesize this might be is because learning words for abstract concepts is hard. If we look at young children's early vocabularies, we see that words for concrete nouns and concrete concepts tend to be overrepresented in young children's vocabularies. So they're learning a lot of words for nouns and concrete concepts, and they're not learning as many abstract concept words early on. And we hypothesize that if learning abstract words is hard, but learning more concrete words is easy, children might be able to avoid the difficulties associated with learning distinct words for abstract concepts by just reusing words that they already know. So if it's hard to learn a word, say for temporal duration, but you already know a word for physical distance, maybe you can just port that word over and reuse it in this temporal sense, rather than needing to learn this word in this more difficult word learning concept. So spatial metaphors may be common because they make the lexicon more learnable and more efficient. To test this, we had 3, 4, and 5-year-olds, so we had preschoolers do a word learning and word extension task where we taught them words for space or pitch and then asked them to extend it to the opposite direction. And critically, we tested both familiar and unfamiliar space-pitch pairings to make sure that children's familiarity with metaphors in English wouldn't be influencing their response. So we tested children with concepts high and low and thick and thin for both space and musical pitch. And our key questions were, is it easier for children to learn words for space than it is for pitch? And how did kids extend these newly learned words, so in either space or pitch, to this untrained dimension? Our paradigm looked like this, and I apologize, I wasn't able to get the sound to sync with Zoom, so there's no sound here. But for children who were trained in the space concept, they would see ones like this box on the left, where we would show them a picture like this, and we would point to one of the balls and tell them this is a Daxi ball, this ball is Daxi, and we would do this twice with 2 different exemplars. And then we would show them a similar spatial arrangement and ask them to point to the Daxi balloon to test their word learning in the initial domain. And there would be feedback on these trials. And then we would give them an extension phase where now we would play 2 sounds that differed in pitch and ask them which sound was Daxi to see if they would spontaneously transfer from labeling the higher balloon as high to also labeling the higher pitch as high. Other children were tested in the opposite direction, so they would learn the word in the context of pitch. So they would hear 2 sounds and learn which of the higher or lower pitch was Daxi, and then they would be asked to extend to space. And half of the children did this with high and low spatial exemplars, and half of the children did it with thick and thin spatial exemplars. What we found was that overall, kids were very good at learning words for space. So for both height and thickness, 3, 4, and 5-year-olds were pretty much at ceiling from learning what Daxi meant in the spatial context. But kids who learned the words in the sound context for pitch had a harder time, particularly for 3-year-olds. So overall, we found that learning words for sound was harder than learning words for pitch. But when we looked at children's word extension results, so their ability to extend that newly learned word to the other dimension, We found that overall kids were pretty good at creating new metaphors, especially 4 and 5-year-olds were extending the novel word consistent with the way these metaphors are used in language without any feedback after this very minimal training procedure. So we found that learning words for spatial concepts is easier than learning words for abstract concepts, at least as it relates to musical pitch, but that kids are very flexible in their ability to create new metaphors online. So to very quickly generalize a newly learned word from one domain to another domain. So spatial metaphors may be so common in part because they make the lexicon more learnable and more efficient. A second domain where we've been looking at the role of these types of spatial associations is in the domain of memory, and particularly within the domain of episodic memory, where we have what happened, where it happened, and when it happened. This when component, this temporal part, seems to be the most difficult for young children. It seems to be the slowest to develop in childhood, and it also tends to be the least well documented in non-human animals. So something about remembering when and placing events in time seems to be unusually difficult. And what we were wondering is whether spatial associations for time, like the mental timeline, may help people remember temporal order. So this is a study that I've been working on with my grad student, Bahar. And you can see we have 67 because we were one undergrad short of our target before we went remote for COVID, of course. But in this task, we used a picture triplet memory task that we adapted from Jenny Passman. And in this task, people saw pictures that were presented from either left to right, right to left, or in a nonlinear order. And we asked people to remember either where or when the pictures were seen. And our hypothesis was that if adults are activating the mental timeline to try to remember when things are happening, then this left to right presentation that's congruent with people's internal representations and the mental timeline should lead to memory facilitation and better memory overall. Conversely, pictures that are presented from right to left or in a nonlinear order are incongruent with these mental representations, and this might lead to interference and worse memory overall. This is what the task looked like. Participants saw triplets of images like this presented one at a time. And the images could be presented from left to right like this, or they could be presented in a nonlinear order like this. And then after seeing 25 of these triplets, so many images overall, we would show them one of the pictures and ask them either where they saw it in the left, middle, or right-hand portion of the screen, or when they saw it within the triplet, first, second, or third. And they did see each triplet twice. So they got a little bit more exposure, but still pretty minimal. And what we found was that in the spatial condition, so where participants were asked where they saw this picture, left, middle, or right, the orientation didn't matter at all. So whether the pictures had presented from left to right, nonlinear, or right to left, people are pretty close to ceiling for this task, remembering where the pictures were. But now when we look at when they were asked when the pictures was seen, so is it first, second, or third, we see a very different pattern. So when the pictures were presented from left to right, congruent with the mental timeline, we see that memory is very good, almost as good as it was for spatial layout. But in these other conditions, nonlinear or right to left, we see that memory performance really tanks. It's just barely above chance, suggesting that when the actual presentation of the images was incongruent with the mental timeline, memory performance suffered. In ongoing work, we're investigating when children begin to show this effect, so the effect of spontaneously activating the mental timeline in memory tasks, as well as looking at whether children who have stronger mental timeline representations may show these temporal memory benefits in other types of temporal memory tasks that don't have an explicit spatial component. Across these different studies and lines of work today, I have tried to make the case that spatial associations for abstract dimensions are shaped by a variety of cultural influences. So both language and explicit cultural artifacts can shape these associations. And the reason that these associations are so common and that they maybe persist and reinforced from infancy into adulthood is because they're actually functionally advantageous. So thinking about abstract concepts in terms of space makes them easier to reason about, which is why these types of metaphors are so common. I'd like to thank you all for listening today. I'd like to thank my postdoctoral advisors at Berkeley who helped get these research lines off the ground, different funding agencies who have supported it, and my current lab at UW.